Hi, everyone. So in this video, we're going to be looking at continuous maps between topological spaces, including notions such as homeomorphisms and homotopy equivalences. Okay, so to start out with, continuous functions are sort of the notion of structure preserving maps in the realm of topology, the topological spaces. So just like how in linear algebra, we look at linear transformations as our structure preserving maps between vector spaces. Similarly, we have structure preserving maps between topological spaces, and these are continuous functions or continuous maps. Okay, and so continuous maps can sort of tell us a lot of information about how topological spaces are related. So to start out with, we're going to define continuous maps via neighborhoods. So if I have any point X in a topological space, a neighborhood around X is just simply any open set containing X. That's all. It's nothing fancy. So now a function F between two topological spaces. So first, this is just a set function between the two underlying sets, X and Y. But we say this function is continuous if, well, it's continuous at a point X if for every neighborhood around f of X and Y. So what we're doing is we're taking this point X, we're looking at its image in Y, and now we're taking a neighborhood around this image. So that's this V right here. We want to be able to find a neighborhood U around X in our domain, such that when we map U into Y via F, the image of U is contained inside that neighborhood V. So we say a function F is continuous at a point if it satisfies that condition, and then a function is continuous if it satisfies that condition for all points. So this is sort of an abstraction of the epsilon delta definition of continuity you might have seen in an analysis class or even calculus. Okay, but now there's another way we can define a continuous function. So that's right here. So here we can say a function is continuous if for any open set, so right, we have a set function f from X to Y, it's continuous if for any open set in Y, its inverse image under F. So that is everything that maps into that open set V here. Everything that maps into V should be open here. So if we take an open set here, its inverse image should be open here. This is also a definition, and you might see this definition more frequently. It's easier to define, maybe a little less intuitive as to why it works, but they are equivalent definitions. Yeah, and so the epsilon delta definition of a continuous function does turn out to be the same as this definition when we're working with Euclidean space. They are equivalent notions of continuous. And then another useful fact is just that if we have a basis for our topology, we only need to check continuity on the basis elements. And that's not too important, but it can save you some work sometimes. Okay, so now homeomorphisms. We looked at these a bit in week 1, but now we're going to actually give them a formal treatment. So a homeomorphism is going to be a continuous map, right? Because continuous maps are structure preserving maps, and homeomorphisms, the idea there is that homeomorphic spaces are the same spaces. So we certainly want homeomorphisms to preserve structure. Okay, so the idea is that a homeomorphism is a continuous function that it should be a bijection. So that is, it has an inverse function, and its inverse is also continuous. So basically, the idea is if we have X and Y, we need to have a function H. This needs to be a continuous map, and it needs to have a continuous inverse as well, H inverse. So a homeomorphism is something that looks like this. Okay, and if there is a homeomorphism between X and Y, we say X and Y are homeomorphic, and we write it like this right here. Okay, so some examples of homeomorphisms, and we'll see some non-examples as well. Okay, so here, these two topological spaces right here are homeomorphic topological spaces. They're both just lines, or line segments really, that are closed at each end. Sure, this one's a little twisty, but topologically that doesn't matter. That's geometric information, not topological information. Now, if we look at these two line segments, this one's bent even more. But again, they're both open on both ends, and they're both lines. So these are going to be homeomorphic topological spaces. Here, these two are also homeomorphic topological spaces, right? They both consist of essentially 4 line segments, all meeting in a point. Two of those line segments have closed points at the end. 2 have open points at the end. They both have that. So they're essentially the same up to topology. And these two are also homeomorphic, right? This is a circle, and this is a sort of bent circle that's sort of bent in the middle, but it's still a circle. Okay, now let's look at some higher dimensional examples. So a square and a circle topologically are identical. You can't tell them apart topologically. So this circle right here, you can imagine sort of just, or maybe it's easier to imagine starting with the rectangle, just sort of pushing in the corners like it was a brick of Play-Doh. You could get it to that circle right there. Now here we have an open sort of blob shape and an open triangle. And these are the same topologically. Right? You could imagine if this was made out of Play-Doh, you could sort of squish it down until it looks like this. Without ripping or tearing or gluing anything. These two are the same topologically. In fact, actually, yeah, these are both just 2 sort of blobs glued together by a line segment. These two are the same topologically, and these two are the same topologically here. They're all homeomorphic in pairs. But now if we look across, right, so this and this are not homeomorphic as topological spaces. This and this are not homeomorphic, certainly, and so on. Well, actually, this and this are not homeomorphic. But it does turn out that, actually, yeah, I guess that's all for the homeomorphisms. Yeah. Okay, so let's look at some more examples. So it turns out that an open ball in RD, so this is D-dimensional Euclidean space right here. And an open ball inside of D-dimensional Euclidean space is actually homeomorphic to the entirety of Euclidean space. You can see this in one-dimensional space via the arctangent function, and you can sort of play around with that idea to get it in higher dimensions as well. Okay, so a sphere. And when topologists talk about spheres, we always are talking about the boundary of a sphere, not it's like a sort of hollow sphere, not a filled in sphere at all. A sphere and the boundary of a tetrahedron are homeomorphic, right? A tetrahedron is like a sort of pyramid shape, and it and with triangles on all sides. And if it's empty in the middle, so it's hollow inside, topologically it's the same as a sphere. You can imagine sort of just like gently smoothing down the corners a bit. You don't have to glue, tear, rip anything to get it that way. And then a sphere with the North Pole, or really any point removed, actually. So this is a punctured sphere. So imagine taking a balloon and just popping it. So it's like a sphere with a hole removed. So it looks sort of like this. Let me try to draw it. Right, so it's the sphere with a hole removed. And you can imagine you take your balloon, you pop it, and you can sort of imagine pulling apart that hole. And you're not actually tearing anything since it was already torn when you got there. It was already popped. and you're just tearing that apart and flattening it out. And what you get is actually a plane. So this punctured sphere here is actually homeomorphic to the two-dimensional Euclidean plane. Okay, so a certain special type of continuous map is an embedding. So an embedding of a topological space is a continuous function such that when you restrict the, so right here we have two topological spaces, X and Y, and we have a function phi from X to Y. But when we restrict, when we just look at the image of phi, so phi is an embedding if phi is a homeomorphism between X and the image of phi, so this phi of X. So oftentimes when we do geometry, we'll sort of work with embeddings of objects, but topology does allow us to work with objects that aren't embedded in any way at all. And you can get some sort of interesting embeddings. For example, this is a normal torus in just three-dimensional space. You could also embed a torus like this. This is actually a trefoil knot. We saw this in the first lecture. Although it's a trefoil knot, not made out of like a string, but made out of a sort of hollow donut. Yeah, so these are two different embeddings, and you would not be able to go from one to the other sort of continuously without ripping anything apart. So it wouldn't be continuous if you ripped it apart. So that's an embedding right there. So the next type of continuous map we're going to talk about are homotopies. So you can kind of think of a homotopy as a path between two morphisms. And in fact, we can make this explicit as well. So let me just give you some intuition first before we go into the detail. So I just want to focus on this top picture right now. So this one right here. So what we have here, this is our topological space X, and this is Y. Okay, so what we have here is two functions from our topological space X, which here consists of just a single point, into our topological space Y. So Y is this torus right here. So a function from a point into Y just picks out a point. So F picks out this point right here, and G picks out this point right here. The idea of a homotopy is that you can think of it as like a path between the two morphisms. So in this case, when F and G are both just picking out points, a homotopy between them is literally just a path. In this case here, where our space or our domain X is a little more complicated, so X and Y. So here we're mapping this interval right here into a sphere, which is Y. And the way it does it is it takes, F takes this interval here to this sort of interval here, and G takes this interval here to this interval right here, or this sort of segment right here. Not actually intervals because we're on a sphere. And now a homotopy between these two functions is sort of a path between the, you can think of it as almost a path between the images, right? So we're sort of sliding this right here down, and we're sort of continuously moving it until we get here. So that's what a homotopy is. Now let's go into the formal definition here. Okay, so we're going to say that two functions, F and G, are homotopic if there is a continuous map H from X cross 0, 1 into Y, such that H, when we restrict it to, you can think of this interval 0, 1 as like a sort of time parameter. So think of this as like time flowing from 0 to 1. And so what this condition here says is that at time 0, H is the same thing as F, and at time 1, H is the same thing as G, and we're flowing continuously between them. So what this means is that we want a continuous function that at time 0 looks like F, at time 1 looks like G, but goes continuously between 0 and 1 across the whole interval. And so that's what gives us the path. oops, this should be, so when, so here F and G are homotopic. So we denote this by F is homotopic to G. Yeah, and so this map H is called a homotopy between F and G. Okay, so let's look at some examples. Okay, so here we have this first example here is, yeah, we're really just going to look at this one example here, which is showing that the whole real line is, really what this is showing is that the whole real line is homotopy equivalent to a point, which we'll see what homotopy equivalent means in a second. But the way this works is that, right, so we have the whole real line here. And so G of X is just the identity. So G takes the real line to itself. It does nothing. But then F of X takes every point on the real line to 0. So we can think of this as F of X here. And what a homotopy should do between these two functions is it should sort of continuously, it should be a sort of a path between the two functions. And so the way this works is that if I pick a point here, X, we'll let G of X is equal to X, but F of X is equal to 0. So basically the homotopy needs to give us a path between X and 0. And we can do this by just simply multiplying by T, right? Because T is going from 0 to 1. So, right, when T is equal to 0, we'll be at 0. And when T is equal to 1, we'll be at X, and we'll be going continuously between the two. So this does give us a homotopy between the two maps, F of X and G of X, which are the identity and a constant map. Okay, yeah, so this is the example. Okay, and so now we can use homotopies to define homotopy equivalences. So the idea with homotopy equivalences that we looked at last week was that it's a sort of loosening of the homeomorphism requirement. Right, so homeomorphism, two topological spaces are identical, really, or they're equivalent as topological spaces if they're homeomorphic. But that's quite a strict condition. So in practice, we're oftentimes going to want to loosen that up. And the way we do that is with homotopy equivalences. So the idea here is that we basically want, so with homeomorphisms, homeomorphism was a continuous map that had a continuous inverse map, a continuous inverse. With a homotopy equivalence, we don't require an actual inverse. Instead, what we require is that the inverse is, or it's a sort of pseudo inverse. So here, F and G are the two maps. So what we have is something that looks like this. So we have X, we have Y, we have F from X to Y, and we have G from Y to X. So if these were a homeomorphism, we would need that F composed with G. So if we did first, G and then F, that would have to be the identity on Y, and we'd need G composed with F. So first doing F and then G, that would have to be the identity on X. That's what it means to be an inverse. But now we're going to loosen that up a bit. Now we're going to say, okay, we don't need those to be inverses on the nose. Instead, we just need them to be inverses up to a homotopy. So that's what's going on here. We don't need G composed with F to be actually equal to the identity. We just need it to be a homotopic to the identity. Similarly, we don't need F composed with G to be equal to the identity. We just need it to be homotopic. So that's really the key difference between homotopy equivalence and homeomorphism. Here we have F composed with G is homotopic, whereas homeomorphism, this would be equal. That's really the big difference. And so homeomorphism is a strictly stronger result than homotopy equivalence, right? If two spaces are homeomorphic, then they are also homotopy equivalent. But the reverse is not true. An example where the reverse is not true is just look at the real line versus a single point. These two spaces are homotopy equivalent. And in fact, actually, the example we did on the last slide showed that, but they are not homeomorphic. And that's actually quite easy to see, right? Because for two things to be homeomorphic, there needs to be a bijection between them. This has infinitely many points. This has 1 point. So there's no bijection between a set with 1 point and a set with infinitely many points. So these cannot be homeomorphic, but they are homotopy equivalent. Okay, so a special type of homotopy equivalence is deformation retraction. So these are stronger than homotopy equivalent, stronger than normal homotopy equivalences are, but they can be quite useful. So if we have any subset of a topological space X, we can look at a retraction map on that set. And so what that is going to do, so the picture here is that we have some topological space X, and then we have some subset of it, A. And so a retraction map is a map from X to A such that right, we're mapping every point in X to a point in A, but we want it to be such that, right, so points in A already are inside X, so they also have to get mapped into A, but we want those to be the identity, right? So we're mapping a point here to a point here, a point here to a point here. We're also mapping points in here into A as well. And we want those to stay the same. So we're mapping this point here to itself, this point here to itself, and so on. That's what a retraction map is. Now, a deformation retraction is a retraction map that is homotopy equivalent to the identity. So this example here is a retraction map, or well, actually no, scratch that. But so for example, a retraction map is, well, actually, this is an example of a retraction map. Or, yeah, this is right here, where we have here our set A would be just the single point here, 0. And then f of x is a retraction map, right? Because f of x maps every point in the real line into A, right? Because it takes every point in the real line and just maps it to 0, which is A. And it turns out that this map is actually a homotopy equivalence. And so this is actually a deformation retraction of the whole real line onto just a single point. Okay, and so a nice result is that if A is a subset of X and X, if A is a subset of X and we have a deformation retraction from X onto A, then they have to be homotopy equivalent. So that's quite a useful result that can be used to prove two spaces are homotopy equivalent, sometimes in an easier way. Okay, so now this is the last thing we'll cover today. So this is a result essentially saying that homeomorphisms and homotopy equivalences are both equivalence relations. This is not obvious. We're not going to prove it, but it is a good thing to keep in mind. Right, so essentially what this is saying is that, okay, if we have two spaces X and Y, and they're homeomorphic, and then we have another space Y and Z, and they're also homeomorphic, then X has to be homeomorphic to Z. So for example, if this is X, this is Y, and this is Z, well, this is homeomorphic to this, and this is homeomorphic to the, actually no, this is not homeomorphic to this. This is homotopy equivalent, but Okay, we have this is homeomorphic to this, and this is homeomorphic to this, meaning these two have to be homeomorphic as well. And same thing, this is homeomorphic to this as well. And then the same thing also holds with homotopy equivalence. So if X is homotopy equivalent to Y, and Y is homotopy equivalent to Z, and X is homotopy equivalent to Z as well. So going from here to here, this is a homotopy equivalence, not a homeomorphism. Same thing here. From here to here, this is a homotopy equivalence, but not a homeomorphism. And this is also a homotopy equivalence. So one consequence of this is that since in particular, all homeomorphisms are homotopy equivalences, we can go from here to here to here to here to here. So these two have to be homotopy equivalent, and same thing, these two have to be homotopy equivalent. And so really all of these are homotopy equivalent, and these are all homeomorphic. Yeah, and so that is all.